Wow, I'm so high up in the sky. I'm standing in a skyscraper right now, and it's so cool. I can't help but wonder though, how do engineers know what materials to use to build something as big as this so it doesn't fall apart? I'm Annika, a second year student studying creative technology and design at CU Boulder. And while I'm way up here in the sky, let's look at one of the things engineers look at when deciding what materials to use when building things, and learn about the mechanics of elastic solids. Whenever an engineer designs something, they have to choose their materials carefully. They have to decide what parts of the thing they're designing have to withstand what forces, and then determine what material works best to withstand those forces. But they don't have to figure out what materials can withstand what forces themselves. Instead, certain engineers will test materials and then publish their findings for other engineers to use. But what exactly are these engineers testing for? They're testing to find a material's modulus of elasticity. And in order to find that, they need to determine the stress present in a material and the strain experienced. Stress is defined as force per unit area, and we describe it mathematically as sigma equals F divided by A. When you push on something, say a block, the stress the block experiences is the force you're applying by pushing divided by the area of a cross-section of the block. If you were to slice the block in half and then look at that cut area straight on, that's the cross-section. We use stress to describe the forces an object is experiencing in order to normalize our measurements of force and account for differences in geometry. Normalizing means standardizing, and it's important that we do this when measuring stress and defining our modulus of elasticity, which we'll get to, I promise, so that no matter what shape you want to use a material in, you know how it'll react to forces. Every material has a specific amount of stress that it can handle before it permanently changes, and that's called the yield stress. Think about this. When you pull a hair tie, it stretches. When you let go, it goes back to its original shape. However, if you pull too far and go past a certain point and then let go, it won't go back to its exact original shape. That's because you passed the yield stress. The next thing we need to know to calculate the modulus of elasticity is the strain a material is experiencing. Strain is defined as deformation per length, and is defined mathematically as epsilon equals delta L divided by L0. L0 is the original length of the object you're looking at. Delta L is the change in length after stretching it. So, if you take a flat rubber band and set it down unstretched, this is its original length. Then, after stretching it, the difference between its current length and original is delta L. Strain is how we normalize the deformation a material experiences to account for differences in geometry, similar to stress. And strain and stress correspond quite strongly. A certain amount of strain corresponds to a material's yield stress, which means you can tell when something is going to be permanently deformed by determining either the stress or strain it experiences. And now, finally, we can define our modulus of elasticity as the stress in a material divided by the strain the material experiences because of that stress, or E equals sigma divided by epsilon. Now do you see why we had to define stress and strain first? It's because they're used when defining the modulus of elasticity for a material. The modulus of elasticity represents the stiffness of a material that behaves elastically, essentially how stretchy or rigid it is. So now we know the theory, but how do we put that into practice and actually find stress, strain, and the modulus of elasticity? Well, that's where testing comes in. Engineers perform tensile tests with mechanical testing systems in order to learn about materials and publish their findings, which we call characterizing materials. Basically, they take a material that they want to test and put it in this machine that has two clamps. The bottom clamp stays still while the top clamp moves upward, and then measures how much force it takes to stretch the material, the stress, and how far it stretches, the strain. Then, the engineers can calculate the modulus of elasticity. When we perform these tests, we want our material to be in the shape of a dog bone, where the ends are much bigger than the middle. If the whole piece is the same size, then the material will break right where the clamps are and give us an inaccurate test. Instead, the dog bone shape concentrates the stress in the center of the piece, so the grips don't interfere with the test. It's also important to note that while the cross-sectional area changes throughout the test, engineers always use the area measured before the test begins when calculating stress. This is called engineering stress. Then, once we've performed the tests, engineers make something called a stress-strain diagram, which tells us a lot about a material. To make a stress-strain diagram, we first have to map stress on the y-axis and strain on the x-axis. Then, for whatever material we've tested, we draw the data we collected from testing the material on the diagram. What stress corresponds to what strain. And voila, we've got a stress-strain diagram. What we see here is the loading curve, which is the line drawn by adding stress to a material and deforming it. As you pull on a material, its stress and strain will change just like the line of its diagram does. There's also something called the unloading curve, which is the line drawn by releasing stress from a material. This line follows the linear part of this diagram, which we call the elastic range. If you look closely, you'll notice that the slope of this linear section actually lines up with the material's modulus of elasticity. And because the unloading curve always follows this line, when a material is stretched only within the elastic range, it'll return to its original form. Past the elastic range is the plastic range. This is separated from the elastic range by our yield stress, which, as a reminder, is the point at which a material begins to permanently deform. When you stretch a material into this range and then release it, the unloading curve still follows the line drawn by the elastic range, but starting from whatever point on the diagram you've stretched it to. Thus, when the stress returns to zero, the deformation does not, and the material remains stretched, now permanently deformed. The highest point on this diagram is called the ultimate tensile stress. This represents the maximum stress a material can withstand before necking begins. Necking is when one part of the material begins to decrease in cross-sectional area while the rest of it doesn't. If you pull apart gum, the very center of it is a lot smaller than the edges. This is similar to necking, but rather than being a very gradual change from wide to thin, necking in most material testing has a much quicker shift from wide to thin. An important thing to remember about necking is that it's counterintuitive. The more you stretch the object, the less stress the object experiences. Think about it like this. If I pull on a little ball of gum, it's kind of hard to pull. It takes a lot of stress to cause strain. The more I stretch it, the thinner the middle gets, and the less of the gum there is holding the two halves together. Thus, it's easier to pull apart, and it takes less stress to cause strain. So, once necking begins, the more strain you put on the material, the less stress that material experiences. And the final point on the diagram is the fracture stress, which is the last stress state an object experiences before it fractures. All materials have each of these points in their stress-strain diagrams. Where each of the points and sections sit exactly is what makes materials different from one another, and lets us categorize some as stretchier than others, stronger than others, and so on. When an engineer is designing something that will have to hold up to stress, they have to take material into account. By looking at stress-strain diagrams and a material's modulus of elasticity, engineers can determine what materials will work for their projects and what won't. And thus, we get skyscrapers like this one, with a steel skeleton capable of withstanding all of the forces of gravity, wind, and everything else. It's important to understand how materials will react to stress before using them to build something. And now you understand the mechanics of elastic solids. Check out the full lesson on TeachEngineering, then use what you learned in the associated activity using Hooke's law to understand materials.